Have you ever seen headlines where scientists look at the exact same data and somehow come up with two totally different answers? Well, today we're going to dig into a crucial choice in research that makes that happen. It really is a tale of two truths. Okay, let's dive right in. You see this all the time, right? One day, a study says coffee is good for you. The next day, not so much. A new drug looks like a miracle in one trial and then just kind of fizzles in the next. So how do scientists sort through all that conflicting information to find out what's really going on? How do they find the signal in all that noise? Well, it turns out they have a really powerful tool designed for this exact problem. It's called a meta-analysis. The easiest way to think about a meta-analysis is as a study of studies. The whole idea is to average out the results from a bunch of different experiments to get one single, much more reliable answer. And this is key, it's not a simple average, it's a weighted average. This means it's designed to give more say, more influence to the studies that are more precise. And that usually means the ones with a lot more participants. Now, as soon as a researcher decides to do a meta-analysis, they hit a major fork in the road. It's a choice between two completely different philosophies about the data. And the first path they can take is called the fixed effect model. So the core belief of this fixed effects model is actually pretty straightforward. It assumes that every single study you're looking at is trying to measure the exact same thing. There's one single underlying truth out there. You could imagine you have, say, 10 different scales, but you're using all of them to weigh the very same gold bar. Okay, so if you're following that logic, if there's only one true effect, then why do all the studies get slightly different results? Well, the fixed effect model has an answer for that. It says the only reason is random chance, or what statisticians call sampling error. Maybe one scale is a tiny bit off, or another one rounds a little differently. They're all trying to measure that one single gold bar, and any differences we see are just random noise. But what if those differences we see aren't just noise? What if they're real? This is where the other path comes in, the random effects model, and it tells a very, very different story. This model starts from a completely different place. It says, hold on, these studies aren't all measuring the exact same thing. Instead, each study is measuring its own unique, true effect. And all of those individual true effects are part of a bigger family, a whole distribution of possible effects. Let's go back to our gold analogy. With this model, we're not weighing one gold bar anymore. Instead, imagine we found a treasure chest with 10 different gold bars. Each one is a little different. Our goal now isn't to find the precise weight of one specific bar, but to figure out the average weight of all the bars in the treasure chest. As you can see here, the random effects model assumes there's a whole distribution of true effects, and we're just trying to find the center of that distribution. And this means that under a random effects model, the results can be different for two reasons. First, you still have that random sampling error within each study, the noise, but now you have a second really important source of variation, the genuine, real differences between the studies themselves. This real variation, the actual difference from one true effect to the next, is what statisticians call tau squared. So, okay, you've got the same 6 studies, but you have these two totally different ways of looking at them. What does that actually do to the final result? Well, let's look at a real example where the same data was analyzed both ways. And this table just perfectly shows the practical difference. Just look at the weights. In the fixed effect model, the biggest study, the Donut study, gets a whopping 39% of the total weight. That's almost 5 times more than the smallest study, Peck. But now, look what happens when we switch to the random effects model. Things get way more balanced. Donut's influence drops all the way down to 23%, and Peck's share actually goes up to 13%. So the big question is, why does this happen? Well, the fixed effect model thinks that big, precise studies are the best, right? They're our clearest look at that one single truth. So it gives them a ton of weight. But the random effects model has a different perspective. It says, hey, even a small, maybe less precise study is really valuable because it's giving us a peek at a different gold bar, a totally unique point in the distribution. It doesn't want the overall average to be completely dominated by any single study, no matter how big it is. And there's another huge difference you'll always see, the confidence interval. That's our range of uncertainty, and it is always wider when you use a random effects model. Why? Because it has to account for two different kinds of uncertainty. You've got the random noise within each study, plus that real variation between the studies. More sources of uncertainty means you have to cast a wider net. Okay, so this all leads us to the million-dollar question for any researcher doing one of these. Which model should you actually use? So it turns out the choice isn't just a statistical one. It's really a philosophical one that depends entirely on your research context. I mean, if you're a company running 10 identical trials with the same protocol, same everything, then yeah, a fixed effect model makes sense. But what if you're pulling studies from all over the world, done by different labs, with different kinds of people? Assuming there's only one single true effect is a huge stretch. In that case, you almost have to use a random effects model because your goal is to generalize your findings. And believe me, this choice has real-world consequences. It can determine whether a drug gets approved or policy gets implemented. And that brings us to this key piece of advice from the experts in the field. For the vast, vast majority of meta-analyses you're ever going to read, the ones that pull together a diverse collection of published studies, the random effects model is just a much more plausible, much more realistic choice. Now, here's a really common mistake that researchers can make. Sometimes they'll run a statistical test first to see if the studies are statistically different, and only if that test comes back significant will they switch over to the random effects model. But this is a big no-no. The experts say the choice should be made from the very beginning, based on logic and the nature of the studies themselves, not on the outcome of some tests that might not even be powerful enough to detect the real differences. So the next time you see a headline talking about a scientific consensus that's based on a review of dozens of studies, you can ask a much smarter question. Are they talking about one single fixed truth that every study was aiming for, or are they talking about the average of a whole universe of different truths? Just understanding that distinction makes you a much more critical and a much more informed reader of science.